Yeah, please sit up straight so I can get this right. Okay, who had that question? Yes?
Number 3 on the whiteboard.
Cool, can you please relay that to me?
It's the second derivative of y plus dy dt, which is just the derivative of y.
I'm sorry, say that again?
Dy dt, 2 dy dt, my bad. So 2, I'm sorry.
Oh, yeah, I gotta take a look, yeah.
Terrible.
It's okay, it's okay. Okay, so here, let me show you how to read that.
Okay.
So that is, I see you were still reading to me the first part of it. Got it. So that's just, I would just say second derivative of y with respect to t. So we could write that d squared y dt squared is just y double dot. And then plus twice the first derivative of y plus 1y, it looks like, equals 0. And then we've got some initial conditions. Cool.
So it's not the same as the second derivative, y.
So yeah, it is. It is the second derivative, but I would just, like, you kept kind of going with it. So you were saying like second derivative of y with respect or something. It sounded like too many words.
Okay.
And it was getting, and I was like thinking you were done with it. So I would just say y double dot, y double prime, second derivative of y. Any of those like rocks the idea. Just real quick like that. So what did you do to start off?
I like what in terms of like lambda, and so lambda squared plus 2 lambda plus 1 equals 0.
Love it. Perfect. And you got your roots out of this.
It was -1.
Yeah, twice, right? Like so. Did you catch that it was a repeated root? Awesome, beautiful. So, what's that? This is web work number 3. Yes. I've got a written assignment I'm going to give you today, just so you can get some practice writing stuff out and get a break from web work. So we have -1, -1. And so my two solutions are e to the negative t. And the second one, what'd you get for the second one?
I got negative, no, just t e to the negative t.
Beautiful. Perfect. Yeah, great. And then we slap some constants in front. And that's our y. So that's our general solution. So if you got that, you're okay so far.
So the derivative, is that like when I try to solve for, I think that's where I messed up.
Okay, let's talk about that then. So this right here, I can use that first condition. Let's just go ahead and do it. That y at 0 equals 3 implies that 3 equals c1 plus, when I plug that 0 in, that dies, right?
Yeah.
So I just get, I'm done. There's c1.
Okay. I didn't catch that.
Okay, cool. Okay, and then for y prime, I'm not gonna work this all the way through, but we'll check our stuff here, Nathan. Derivative of that with respect to t, and remember, do not absorb. Don't absorb this when you're doing this process. That's like, I would say the only time to absorb is when you're doing separation of variables. Everything else we're gonna do, it's just gonna mess stuff up. So you do this one, and then C2, and you do that derivative with the product rule. So I'm doing C2 times the product, derivative of that product. So T. Look good? And then put your 0 in here, and then 7. So 7 equals this right-hand side with t replaced by 0. And since you got C1 already, you could even put that in here, and you'll get C2 immediately. Does that all sound good? Yep. Cool.
Thanks.
You're welcome. And the other, yes, Chris?
This is from the new web work they just assigned us.
Okay.
It's second derivative of y plus the first derivative of y plus 1 equals 0.
Ah, yeah, good one.
Yeah.
You want me to talk about that? So what did you get for, see, now I'm getting old. I like the way you actually said it. You looked like a wizard summoning something. You were like this orb of power or something. As you said it, y, double prime. Okay, go. So what was our characteristic polynomial?
Well, my first impression was to use a quadratic formula,
Okay, but what is the polynomial first?
I said lambda squared plus lambda plus 1 equals 0.
Beautiful.
Yeah.
I knew you could get there, I just
Yeah.
wanted, for the narrative. So, yeah, quadratic formula.
Okay.
Yeah, this involves like the golden mean. It shows up in this, so it's not the kind of thing you guess. So you got b squared minus, well, actually, this one isn't the golden mean, I guess. If there had been a minus there, we would have got it. And then over 2, does that all look good?
Yeah, yeah.
So that's -1/2 plus or minus root -3/2.
Yeah.
And that, now I've got an I,
Yeah. Yeah.
like so, yeah?
Yeah.
And one of the first things I was gonna do today was put a little table up just to refresh everybody's memory. But if I had, and I'll start it right now. So if I have this root, then I have these solutions. If I have alpha plus or minus I beta, then I have solutions corresponding to that e to the alpha t cos beta t and e to the alpha t sine of beta t. You get both of those in there. So from there, then Chris, I mean, you can literally just plug in these values
Yeah.
and you're good to go.
Okay, that makes more sense. Thank you.
You're welcome. Anything else to chat about? Yes.
Number 6.
Yes. Sorry, I'm gonna go ahead and start telling me about it, 'cause you're a look for a,
Okay.
there we go, yeah.
It's the second derivative of y
Okay,
plus 6 times derivative of y
okay, so that's it.
plus 9y equals 0.
Cool, looks like a double root,
Mhm.
yeah? So we've got, I've been making people say these, but it's pretty clear, everybody knows how to do this. It's, it ain't the hard part of all this.
Mhm.
So then, what did you factor into?
The lambda plus 3 squared.
Cool, so we get lambda equals -3.
Mhm.
Yes, so what was your question? Like, where to go with that, or?
So I just don't know if I was making the same mistake over and over again.
Ooh, that's not fun.
No, it's not fun. But doing the derivative and the initial conditions. So the initial
Oh, okay,
conditions
yeah,
here,
let me get those.
it's y of 1 actually.
Oh, cool, okay, that's exciting, it's mildly exciting. What was y at 1?
0
Ooh,
and 1.
ooh. Fun, okay, yeah, that really shakes things up, and I can see why you might be a little uncertain about it. So let's say my roots, just to not take all of your fun away, I'm gonna change the problem just a little. This is my problem, very much like Kipker's problem. So I got -5 and -5. Okay, so my general solution is C1 e to the -5x. It looks like we're using x because of the primes. Plus C2 x e to the -5x because of a repeated root. Yeah?
Yeah.
All right, so then y of 1 equals 0 tells me that 0 equals C1 e to the -5th plus C2 e to the -5th. That's interesting. So this won't be pretty. And that's probably what you were like, this can't be right, it's so ugly. But it's gonna have e's as coefficients, I think. So then y prime, I have to do that derivative first, is -5 C1 e to the -5x plus C2, and then we do that derivative with the product rule, like so. And then I plug in 1, and I get 1 out, so I've got -5 C1 e to the -5th. I'm gonna help you see how to make this much easier. Definitely got a good thing to help with. And then C2, plug in the 1, and I get -4 e to the -5. Yeah?
Yeah.
Okay, so notice how, actually, there's a couple notices here. But the first notice is that this equation here, let's rewrite it. So we've got 0 equals C1 e to the negative fifth plus C2 e to the negative fifth. I can annihilate that e to the negative fifth, right? So I just multiply through by it. So literally this says the same thing as that. So C1 and C2 have to be opposite sign. So we got that. And then this one down here, I'm going to multiply both sides by e to the fifth. That's the thing I think will help. So if I multiply both sides by e to the fifth, I get an e to the fifth here, and then these nasty buggers go away on the right. So the second equation is going to be e to the fifth equals negative 5c1 minus 4c2. And I think from there, maybe I would take it. Does that sound pretty good? I'll go ahead and finish this for everybody. But check this out. C1 is equal to negative C2, so you can easily convert this. I'm going to replace this C1 with, or C2 with negative C1. So this equation becomes e to the fifth equals negative 5C1 plus 4C1. Oh my God, that's so nice. E to the fifth equals negative C1. C1 equals negative e to the fifth. C2 is the opposite. And then when you write your solution out, it's not going to be pretty. So your solution, but you could make it pretty. So let's write it out. My particular solution is going to be negative e to the fifth e to the negative 5x plus e to the fifth x e to the negative 5x. And what you could do, Kidra, is combine with exponent laws just to make it a little prettier. So this one here would be e to the negative 5. Look, I can do that. That's pretty. And I could do the same thing over here with a, oh wait, what am I doing? I'm being cucamonga. This should be minus, this should be 1 minus x. And just a 5 there. Yep, okay. Plus x e to the 1 minus x, 5 times 1 minus x. Yeah, something like that. Does that make sense?
Yeah.
So what do you think was going wrong with yours?
I think that when I got to the step right before that, I was like, that's so many x's I don't know what to do.
Oh.
And so I combined, I don't even know, I couldn't even tell you what I was doing wrong, but
You feel better now.
I feel better.
Wonderful. Any more medicines needed? Math medicine being dispensed freely. Yes? Hans?
The next one, number 7.
Okay. Please read that to me.
The fourth derivative of y minus 10y, the
Second
3.
derivative?
Third derivative,
Third.
My bad.
Ooh.
plus 25y, second derivative.
Wow. Okay, cool. Equals 0?
Yes.
Awesome. What'd you get for your characteristic polynomial?
I would have got lambda, is it the third or fourth?
Fourth, it always matches the derivative level.
Okay, got you. And then negative 10 lambda 3
Mhm.
plus 25 lambda 2.
Beauty. So, in terms of factoring this, what was your first move?
I didn't get this far. I saw
Okay,
the 4 and I
gotcha.
was like, I will simply do this later.
Oh, okay. So, just like we're talking about this, can somebody tell us what the next factoring move would be? Pull lambda squared out, yeah. So pull that out. Don't divide by lambda squared, because if you do, you've just tossed away 2 beautiful roots, 2 zeros. So keep them all here for posterity's sake and math's sake. What about this? What would we do there? What you think?
Factor it, so it would be lambda minus 5 squared.
Beautiful, nice, very nice. So we've got a repeated 0 and a repeated 5. Chris, yes?
I just have a quick question.
Sure.
About the solutions up there.
Yeah.
Is there C1 in front of the cosine and C2 in front of the sine?
So the way I'm going to write this up, you could always assume that.
Yeah.
I just like writing them this way because it might be that there's a C to the 9th here and a C to the 10th here, because we
Okay.
don't know, so like,
Okay, that
yeah,
makes
yeah.
sense.
But each one of these gets an arbitrary constant
Cool, thank you.
of your choosing.
Dr. T,
Yes,
so is it allocated zero because lambda is squared?
so I have 0 twice,
Yeah.
and then 5 twice. Does that sound good, Hans?
Mhm.
Then take it from there with, yeah. Some good head dancing. All right, anything else? Good, I've got some fun games for us to play today. Here's my first one. Well, actually, my first one is I wanna make a table for you, so this is all like cogent and, put into one place. Before I keep going on with this, is everyone cool with the procedure? Like where these roots are coming from that I'm talking about? Because I will put the steps on the board if we're not. Okay,
You know, I'm not fine.
you're good?
I was just thinking, yeah.
Oh, you're saying, okay. So get your characteristic polynomial, find the roots. If the roots are this, these are our solutions. So let's make a full table here. So if I have distinct, just lambda. Just a lambda by itself, it's not repeated. Let's say lambda not, actually, to make it nice and solid, apart from our variable over there. Then I just get e to the lambda naught t. Notice this case actually gets you that, right? Because if beta is 0, then you just get the e to the alpha t. So there's nothing mysterious going on with that. It's like everything here is consistent, is what I mean. If I have a repeated lambda naught of multiplicity m, and multiplicity is just the depth of the 0 over there. That 0, both those zeros had multiplicity 2, multiplicity m. Then I'm going to have e to the lambda naught t, t e to the lambda naught t, t squared e to the lambda naught t, all the way up to t to the m minus 1. You can think of this as there's like a 0th power of t right here. So we started counting at 0, e to the lambda naught t. See, so we got complex roots, we got those roots. That pretty much freaking covers it, except I want to talk about repeated complex roots. So this is a repeated real root. And so you could actually just insert a repeated real lambda naught. So here's a repeated complex root. And then once we have this, we can do everything. So let's say I've got alpha plus I beta, multiplicity m. Then I'm going to have those two solutions. And like Chris was asking earlier, I'll put a C1 here or whatever I want in front of it, and then another constant in front of this. But these repetitions just mean you're tacking on extra t's or x's or whatever you have. So the next one's going to be t e to the alpha t cos beta t, t e to the alpha t sine beta t. Both of these. So if I had this root repeated twice, I had 1 plus I multiplicity 2, I would have 4 different things to add together. Then you keep on going till you get to t to the m minus 1, e to the alpha t cos beta t, and t to the m minus 1, e to the alpha t sine beta t. That takes care of everything. You've got it all right there. There's no other kinds of roots to polynomials. They're complex, or they're real, and they're repeated, or they're not. Is there anything I can clarify there? I'm seeing some semi-furrowed brows. I thought Kitra had a furrowed brow.
So it's
Yes, you did. I knew it. I knew it.
so it's multiplying. So
Yes.
Okay.
Yes. So that's powers of t, an extra t for every for every repetition, tack on a power of t, or tack on an extra t. Yes.
In addition to both of the
Yes.
solutions. Cool.
Yes.
Is there supposed to be a sine beta t?
Yeah,
Did I?
the first one.
Yeah, thanks, good call. Absolutely, there is. One thing I do want to point out is that in this special case here of zero roots, that's where you get your pure polynomials from. So just make a note to yourself that when you have zero roots, so zero roots give, and I don't mean that's like no roots, but roots that are zero, give polynomials. So if I just have 0 multiplicity 1, right here, multiplicity 1, I just have, that's just a constant, 1. And I would tack like a C1 times that. If I have 0 multiplicity 2, I've got 1 and t. And just so you're like, where's that 1 come from? Just to remind you, it's e to the 0t. You would tack that on. So there's nothing weird, it's not a strange case. It's just a thing that happens a lot that I want you to just have a nice rule for. If I have 0 multiplicity m, then I'm going to have 1 t squared on up to t to the m minus 1. That's it. That's the gamut. I want to play a different game to practice this. Where's my game? Back here, here we go. I'm gonna give you a solution, and I want you to write a differential equation that it's the solution to, that it could be the solution to. So given, we're gonna play this a couple of times, y equals x plus 2 sine of 3x minus cosine of 3x. That's the solution to some differential equation. What differential equation? So give me the smallest differential equation that could be the solution to. So give a diffie-q that this could be the solution to. You don't need to give initial conditions or anything. So be a particular solution to. How are you going to approach this? And these all could have said, realize over here that these t's could all be x's if x were the independent variable. How would you approach this problem? So spend a moment. What are you thinking here?
Thinking.
Yeah, okay, good. I'm sorry to put so much pressure on you. Hold on. Yeah, so Vivian just said, well, there's a sine and a cosine in there, so we know there's a complex root, right? These come from complex roots, so that's a good call. And they always come in pairs, right? So if I've got a sine of 3x, there was a cosine of 3x that could have been there. It's just got a 0 in front of it. What root, so let's write this out here. If I have cosine of 3x, sine of 3x, what's the e that's in front?
0.
E to the right, so there's an e to the 0t in front, yeah, or 0x, excuse me, in front. So what's the root?
3i.
0 plus or minus 3i, perfect, nice.
Is that it?
What?
That's not it, right?
That's not 8?
No, that's not it, right? Is that it?
That's not it, that's part of it, that's
Oh.
one. We're not done, no, we haven't, we're building it up,
Oh,
Chris. Yeah, it's like, that would be a bad day probably. You'd be like, well, I don't understand anything. We're not even close to done, we're just heading there. How do I get x? Where does x come from? What root?
From having repeated roots
Thank you. Of what?
of real root. or
Yes, of
zero.
which number?
Of 0.
Of 0. So check this out. 0 gives us 1t, t squared, t cubed, or, you could put in here 1x, x squared, whatever. So polynomials polynomials come from zero roots. Let's write that up here. Polys come from zero roots. The first zero root would give me just a 1. The second zero root would give me the x. So I've got 4 roots to deal with. And luckily that one just comes as a pair. So the differential equation that would have this as a solution would have these roots, right? We're just working backwards. If I said to you, hey, here's the roots of a differential equation, give me the solution. Hopefully what you would do is come from here and go, all right, let's see, so that's e to the 0x cosine of 3x and e to the 0x sine of 3x. And then this would give me, let's see, the first 0 would give me a 1, the second 0 would give me an x. And then I would string those together with constants. So I would get y equals c1, and I'm not going to write that e to the 0x there, cosine of 3x, plus c2 sine of 3x, plus c3 times 1, see that's just a constant, plus c4 times x. So now I just have to come up with a polynomial that has those roots. So we were far from done, Chris.
Okay.
So these are the roots.
That's
So step 1 is find the roots required. Step 2 is construct a polynomial. So here's the rule here. Rule. If lambda naught is a root of polynomial p of x, or p of t, then p of x is equal to x minus lambda naught times some other polynomial stuff, other factors. But I know that i.e. lambda minus lambda naught is a factor. This should say lambda, excuse me. Got a little excited there. Is a factor. So, if I've got lambda, if I've got 0 and 0, that means I've got lambda squared as part of my polynomial. So this gives the 0 twice. I've got a plus or minus 3i, so I'm going to have lambda minus negative 3i, and I'm going to have lambda minus positive 3i. So now check this out. If I gave you this polynomial in nice factor form, you can tell when lambda equals 3i, that's a 0. When lambda equals negative 3i, and when lambda equals 0, that's a polynomial. That's a 0. Then you have to multiply this stuff out. So the lambda squared is not a problem, and here we're going to do first times first. The outer is going to be minus 3i lambda. So you get to mess with I. And that's always fun. And then the inner, so this first, let's foil this sucker. The inner is going to be plus 3i lambda. And then the L is going to be, what is the L? What is the L here? So we've got positive 3i times negative 3i. What is that? What? Negative 9i squared? Yeah, yep. So we've got minus 9i squared, but I squared is what? Negative 1. So this becomes plus 9. So my polynomial is going to be lambda squared times lambda squared, these cancel, plus 9. There's my characteristic polynomial. Now I can construct the diff-EQ from there. I just got to multiply it out because we don't get our diff-EQs in factored form. So I would expand. So let's see, what did I got here? 1, find the roots required. 2, construct the characteristic poly. Step 3 is expand the characteristic poly. And that's easy here, that's just gonna be lambda to the fourth, wow, lambda to the fourth plus 9 lambda squared. And then translate the powers into derivative levels. So we're just going backwards. Step 4 is translate to a diff EQ. And so that's going to be fourth derivative of y plus 9 times the second derivative of y equals 0. And if I asked you to solve that, you would do all of this backwards and come up with that. But I want to do this because I think it strengthens like your skill at doing both ways, right? If you can do something backwards, you sure the hell can do it forwards. And you're going to need to do it backwards real soon anyway. So, let's try one together. Is there any questions on this before I erase anything? No? All right, your turn. Give me the differential equation for which, so here's the solution, y equals 4x e to the x sine of 2x. What differential equation has that as a potential solution? Go forth. Today is complex variable day. Complex value day for sure. One thing to keep in mind is that 4 doesn't matter to you, right? That 4 does not help you. It's the variable patterns that help you. Oh, I haven't walked around in ages. I'm going to do my walk around. It's been so long. Travel well, my friend. Thanks. Have the recording up later. Thanks, good to see you. Oh gosh, somebody's jacket fell or something.
Oh, that's fine.
Okay. That looks good.
Okay.
Yeah, exactly. And you might as well just put a plus or minus in the middle, because they always come as a pair, so I would just write, once you realize a complex pair has kicked in, just do the plus or minus right off the bat, just write them as a pair. They never appear by themselves unless you actually have complex numbers as your coefficients, which we don't. Little signs along the way, right? Just so we're making sure that X means something was repeated. It doesn't tell you what, that's what the other part tells you. And everybody's wearing shorts, and I'm like, I've got like a parka with me. Like a weirdo. As usual. we get a sanity check on the root? Grace, what did you get for the root? I know you got it.
0, 0, 1 plus 1 plus 2.
Oh, that's interesting. Okay, wait, what you said, did you say 0, 0?
Yeah.
So this would only happen if I had a pure x by itself. So this x here tells me that the thing that was repeated was whatever corresponds to that root. So it's not a 0 that was repeated. I'm super glad we had that conversation. But what was it? Because you had that complex root. What did you get?
1 plus or minus 2i.
1 plus or minus 2i. So I look at this, I say, okay, look, that's my root, 1 plus or minus 2i. The x in front here says that happened twice. If that were an x cubed, I would know it happened freaking how many times? If this was this, how many repetitions? 4. God help us. We don't have that. So this, here's my roots. 1 plus or minus 2i, 1 plus or minus 2i. So your polynomial looks like that. But that's a bad way to do it. Let's get it all out here. I would definitely recommend multiplying conjugate pairs together. So like do that and then do that. Don't like square one and then square the other and then multiply them. These are meant to, these are built so that things will cancel nicely if you do them in this raw form. And I want everybody to do this today just so that we're together when we're doing it. Yes?
Does it matter that there's no cosine, or does that become relevant later?
It doesn't, so it doesn't matter because what an awesome question, Kitra, because what that means is that there might be one, but it has a 0 in front. Because these numbers in front, these are the C's we end up solving for. And we're just saying, oh, they've been solved for, and apparently there's like a 0 in front of the companion for this. And in fact, there's zeros in front of all the other, there's a 0 in front of this. And there's a 0 in front of this. We're thinking like, what is the most general possibility? So, great question. This will be quite a something. Yes, Hans?
Did you multiply like the first two and the last two, or did you multiply the ones that were plus and the ones that were minus?
I'm doing them like this. So yeah, just do the conjugate pairs together, because then things, if you don't, things will be really unhappy, I think. Very messy, anyway. And I think I did that correctly. Now we gotta do that, which I'll start getting on. insane. Like definitely not guess worthy. I wouldn't have guessed that. And let me know if is anyone else getting something like what I'm getting? I hope I'm the fastest polynomial multiplier in the room, but I might not be. I'd like to think of myself as that though. Did you get that same thing as me? Cool, awesome. Yeah. Yep. Yes, exactly. Yeah, well said. Absolutely. We got that one done. Let me give it one more quick one. Just tell me what the roots are. You don't have to do the whole dang polynomial. For that one, just what are the roots that corresponded to? So that's 1 minus t cubed plus t squared e to the negative t. What are the roots and their multiplicities? Remember, think of this in its most general form. Let me help with that. That's where that would be coming from. The zeros hide the lesser terms. Ella, ask me a question.
I think that's what I was confused, like, I was confused with the last one, where that equation came from. I don't, like, where did that come
Which,
from?
I'm sorry, which? where?
The longest one.
Oh, God. Oh, that one up there. Oh, got it. Yeah, so these things we're looking at are after you've gone through the whole process we've been doing, you get your C1 plus C2 plus C3 plus C4 plus C5, C6, C7. You've gone through the process and you've come up with this. Then you've got some initial conditions like y at 0 is this, y prime at 0 is this, and you solve those and you end up with that because some of these things died off. That's what we're getting at. So what we want to do is think, where could this have come from? And it could have come from something like this. Now it couldn't have come from this because I don't have a TQ possibility. So it's coming from the greatest possible the greatest possible expression that I can have where I'm allowing things to be 0.
Got it.
Does that help?
Mhm.
Yeah, cool. What are my roots here? What's this whole thing correspond to?
0.
0, how many times?
It would be 4 times.
Yep, 1, 2, 3, 4. What about this? What root? -1, how many times? 3. The first -1 just gets me regular old negative e to the negative t. The second repetition gets me a t in front, and the third one gets me the t squared. So what order differential equation would this be? 7th order, yeah, exactly. It'd be a 7th order DE. Don't worry, we're not going there. Can I answer any questions about this, or would you like to do another one? Let me know. Another one? Is that what you're saying? Okay, cool. Got it. All right, so one last one here. Let's do y equals cubed cosine of t do not come up with the differential equation, please. Just the roots. You already got it.
I said one.
There you go. There you go. God, I don't want to write out where this could have come from, but oh well. Parentheses now. Lots of zeros, right? Kitra, what root do we have here?
Plus or minus I.
0 plus or minus I. So when you have a pure trig function, that's a pure imaginary. So just keep in mind, we have e to the alpha t cos beta t. That's for alpha plus or minus I beta. But a good, just in your head rule of thumb is that a plain trig function has no real part. So that's just plus or minus IB. Same with sine of cosine, or sine of beta t. So for this one here, remember the powers of t tell you the repetition. The thing to the right of the t tells you the root. How do I get a cosine? Well, I have 0 plus 1i. So this thing here corresponds to a 0 plus or minus I. Here's the first 0 plus or minus I, right here. Here's the second 0 plus or minus I. Here's the third 0 plus or minus I. And here's the freaking fourth one. 0 plus or minus I. So this was 0 plus or minus I multiplicity 4. And that would, now that I just feel like having my jollies, plus or minus I is a root of this thing. And we have it to the 4th power. And so our diff EQ would actually look like this. I guess I'm just showing off now, probably. That would be our full polynomial. You could get the diff EQ from that. Questions? Chris, did that help a little bit? And you're gonna get tons of practice with it, don't worry. Yes, Ella.
Where did the lambda squared plus 1 come from?
So that is, I just know that that has plus or minus I as its solution. So when I look at that, right, let's see.
Oh.
Does that make sense?
Yeah.
So lambda equals plus or minus I. Good question. Good stuff. All right. Why the hell are we doing this? It's not just to practice, and it's not just for me to show off that I know Pascal's triangle, which is not much of a show off. If I can find my eraser, that'd be a better thing. Because we now completely own every homogeneous nth order linear equation with constant coefficients. We can do all of them. But what if they're not homogeneous? And that's the part we're gonna do today. So far we've, we had 0 on the right, everything was hunky-dory. So let's now talk about the non-homogeneous case. And let me motivate it with an example and show you what the plan is here. So let's see here, I got one written out. I've got y prime, oh there we go. Y prime minus 3y equals x plus 2. Oh boy. So here's the process, and I'm gonna do it I'm gonna write out the process here for a specific example and then give it to you in general. So the plan is this. We're gonna break the problem into 2 parts. So we have a 2-part approach. Part 1 is to solve the homogeneous problem. Homogeneous version. So in other words, just replace the right side with 0. The other cool number. So we solve that. Can you solve that in your head? I bet you can once you get used to it. See if you can just do that in your head. You can do it on paper if you want. What's the polynomial? Lambda minus 3. What's the root of that? 3. So what's my solution? E to the 3x, beautiful. Very nice. So Olivia cranked this out in her head. She said, okay, well that's lambda minus 3 equals 0. That's the characteristic poly. And so lambda equals 3 is the root. Single root, not repeated. So e to the 3x is my independent variable. There is my solution. So what I'm going to say is, I'm going to write y sub h equals c, and I'm going to put a c1 there just to prepare for future traumas that we're going to have where there's more than one c. This stands for homogeneous. Now we're going to think about this in an interesting way. This left side takes functions and does something to them. So this left side is an operator. And I talked about this a long time back, but it's really important. If you understand what I'm saying now, it's going to make this all so much easier. Oh, I thought Chris was going
Oh, no.
stay on the operator.
I didn't really get
don't go
operators.
there. Somebody's had a lot of trauma with these things. So I can think of this left side as a thing that eats y's. Y equals a function of x. It eats a function, it takes its first derivative, and it subtracts off 3 times the function itself. So when I put this function in, when I feed this into the left side, what comes out? 0. When I take this function and I find its first derivative, and I subtract off 3 times its original version, they cancel. So this left side eats e to the 3x and produces no waste. Nothing comes out, it's all going to muscle. What do I have to feed it so that it spits out x plus 2? That's what we need to figure out. So, what roots, if this was your solution, now we come to the game we just played. The left-hand root was -3. We need to figure out what the right-hand root is, and this is step 2. Step 2 is we're going to find the particular solution. And this is called y sub p, which spits out x plus 2 when we compute yp prime minus 3yp. I want to find some function so that when I take its first derivative and I subtract off 3 times the original, I get that out. So now we got to play the game. The plan here is, approach, list the roots that would correspond to the right-hand side, RHS. What roots correspond to the right-hand side? Let's see, there's no e's, right? So there's no like 1s or 2s or things like that. There's no complex, there's no cosines and sines. Very happy. What roots would that left side be the solution?
The distinct lambda?
So wait, say that, wait, oh, sorry, so can you, are you asking a question or are you saying?
A little bit of both.
It felt like that.
It's the distinct lambda, lambda naught.
So why are you saying that? I'm curious.
Well, because in my notes I have when that's the case, all we have is the solution e to the lambda t.
Yes, but we don't have any of those. So we do have distinct roots, but what root? And actually we don't have distinct roots because we've got a power of x, right? The fact that there's an x here says something was repeated. What was repeated? 0. 0 gets me a constant. I don't know where the fuck it went. So this corresponds to the first 0. This corresponds to the second 0. So 2 zeros would give me a polynomial of the first order. I'd get a constant and an x. So it corresponds to the right-hand side, 0 and 0. What would that look like? So you come up with those roots and then write, you need to write these roots down first, but write the general form of a solution corresponding to these roots. And we're going to use new letters too now. We're going to use A through Z to these roots. So the first root gives me a constant. So let's put them down here again. That gave me a constant, 1. I'm going to tack an arbitrary coefficient in front of it. The second root gives me x. I'm going to put a b in front of it. And I'm going to add those together, and that's my particular solution. So my particular solution is just like the stuff that we've been doing before. We're just really working things backwards. Forgetting about the left side, looking at the right side, thinking what roots did that correspond to, and then writing the most general form it could have come from. So this is yp. That's my guess. And let's think about this. I wouldn't expect the thing that I fit in here. Like if I had y equals like e to some power. When you take the derivative of e to some power, you still get e to some power. So there's no way this could annihilate the e. The only thing that y could be to spit out a polynomial is a polynomial. Polynomials have derivatives that are polynomials. So yp must have been a polynomial, and this is the most general form we need right there. So now we make that guess, and don't worry, we're going to do this a bunch. I know how you're looking at me. I see. Don't worry, I got you. So step 3 is to plug. Okay, I'm sorry it's red, but it works. Plug yp into the Diffie Q. And then simplify and compare to the given right-hand side. So in other words, I'm going to take this guess. I'm guessing. This is really a guess. This is how you make an educated guess. Yp must look like that. Find the first derivative. Easy. Plug that into the left side. So then yp prime minus 3yp equals b, that's yp prime, minus 3, use parentheses, a plus bx. And I'm gonna set that equal to the given right-hand side, x plus 2. I just need to figure out what a's and b's make this true. So simplify. This becomes b minus 3a minus 3bx equals x plus 2. Can somebody tell me? No, we're about ready. What does negative 3b have to equal for these two things to be the same? And what does b minus 3a have to equal for these two to be the same? So the negative 3b, yeah, what do you think that needs to equal, Lavina? Is it? Yes, so the coefficient here, it's gotta equal that, right?
Sorry, I was thinking of, yeah.
That's okay. Oh, you were doing this one first. Okay, well, okay. But- No? Okay.
I was doing B, but I forgot it had a negative 3 in front, so
Oh, that would do it.
should be 1.
Got it.
Yeah.
Got it. So negative 3b must equal the 1 in front of the x. And then b minus 3a must be the 2. And now that's easy, right? So b is negative a third. And plug that in down here. Let's see, so we get negative 1/3 minus 3a equals 2. So negative 3a equals 7/3. And then a equals negative 7/9. And we just found our particular solution. So yp equals negative 7/9 plus or minus 1/3 x. So look at it, let me go through it again. Step 1 is solve the homogeneous problem. Forget about the right side, put a 0 there. Step 2 is only think about the left-hand side. Step 3 is take that generalized thing that would give the right-hand side and figure out what coefficients it needs to have. And then step 4 is our final solution is going to be y equals the homogeneous one plus yp. I haven't talked about initial conditions yet. That's because I'm trying to be kind. So we'll just hold off on that for a second. But here, our final solution is the homogeneous one. So C1 e to the 3x minus 7/9 minus 1/3 x. You put that sucker in, no matter what C1 is, it works. Yes, Thomas?
Yeah, sorry, I missed why is the final solution equal to y, or the homogeneous one plus the particular
Cool.
solution?
Yeah, good question. So we're gonna take this thing. We found the solution that this consumes, right? So there's this whole general collection of things that never makes it out, but still is a solution. And because this equation is linear, this is it. So let's say I have a linear differential operator, like say d of y equals y prime minus 3y. I have this thing here. That is linear. So if I take d of yh plus yp, I get d of the homogeneous solution plus d of the particular solution, and this piece dies, and this piece gives me the x plus 2 or whatever is over there. So this is allowing for the greatest possibility of things. We don't want to forget about all these pieces from the homogeneous solution that just don't show up on the right-hand side. We would be throwing away a good portion of our solution.
Yeah.
Does that help kind of see why?
I think, yeah, that kind of makes sense.
Other questions on this? I wanna do another one. Alright, let's do one more. I'll do this one with you again. So let's say I've got y double prime plus y equals cosine of x. It's gonna get weird. Step one, find your homogeneous. Can you do that for me, please? Find YH. So that's gonna be the solution to this. Make sure to record the roots. You definitely wanna have a little, I would put the roots underneath this side because we're gonna wanna see them when we think about the right side. I hope the recording's still going. I was worried about that. It is, oh, one. What are the roots on the left side? I'm sorry, what? I, plus or minus I. We've seen this, boy, it's getting loud out there, isn't it? I can barely think of that kind of stuff goes on. Does it make sense to everyone that the roots are plus or minus I? It might have taken a little while longer, but this is your characteristic polynomial, and those are your roots. So what's YH look like? What solutions does plus or minus I correspond to?
Cosine of x and sine of x.
Beautiful. And there's like an e to the 0 x in front, right? It's not showing up. We got a pure imaginary, we got pure cosines and sines. So this is gonna be c1 cos x plus c2 sine of x. What roots correspond to the right-hand side? So let's write this out. So we got plus or minus I on the left. Where does something like that come from? What kind of a root would you have? Plus or minus I, right? So there's a plus or minus, so we've got like the same root repeated on the right. Now watch this. I know that I can't do this. So for step two, when I come in, so the right-hand side roots, let's just write out a couple things here, are plus or minus I. If I do this, if I say y particular equals a cosine of x plus b sine of x, will this pass through and give me a cosine out the other side? What will happen if that left side eats this? What happens if I take yp double prime here plus itself? What do I get? T time. Get T time.
There'll be a sine equation in it.
Say that again.
There'll be a sine equation in it once it's plugged through.
Ooh, can you explain what you mean? I don't quite know.
Well, you said you're taking the second derivative of that.
So let's do that. Yeah, right. So we got that. So that's going to be negative a cos. Yeah, like that changes sign once, right? And then minus b sine of x. So there's our second derivative.
Mm-hmm. And if you plug that in,
Yes. What do I
there's
get
still
out?
the sign.
When you say
Oh.
there's not quite. They cancel,
I see.
right?
Yeah.
So I can't just go, oh, look, there's a plus or minus I on the right, so the particular solution must look like this. I can't, because this gets consumed by the left-hand side. It's gotta be heavier. It's gotta lay, It's gotta poop out something solid, like right now, there's just gas coming out. We wanna feed this thing heavily, lots of fiber. So what we do is we think of this is like the second occurrence of plus or minus I. So I count multiplicities. When I'm doing YP, I count the multiplicities of the right, including the ones on the left. So this is the second occurrence. So this repeats a left-hand root. So I've got to act like it's the second occurrence, because if I just let YP be this, nothing comes out. So what we do is we say, okay, well, let's just keep on going here. What would come next after this? You would have A x cosine of x plus B x sine of x. So I keep building YP off of YH. You don't forget any of this. You remember this and then keep building. So if there's repeats, you have to include them down here. Chris, you had a question?
No, that made sense to me.
Okay, wow, awesome. Definitely feeling better about the looks I'm getting. I don't think I have to worry about walking to my car now. So, I've got a couple problems for you. I don't have time to write them on the board. I'm gonna type them up real nice and put them in world class for you. They're gonna be handwritten problems that would be great if you could try before Monday and then come in on Monday with lots of questions. Sound good? Awesome, beautiful. Yes, sir.
How do you know that that's the final particular solution? Like, why wouldn't it go further than that?
Oh, what a great question. I could, but we want to try to minimize our suffering.
Okay.
So we just go for the minimal energy solution. This is all I need to get out a cosine or a sine.
Got it. Okay.
Yeah,
Thank you.
awesome. Cool. Alrighty, friends, that's a lot of heavy stuff. Thanks for bearing